Evening all. Now, I had a problem with Sing 2. That problem is there's nothing to complain about. It's a feel-good musical that feels like a natural extension of the first movie. While the new characters are a bit generic, the stock characterizations that they provide do flow naturally into the movie for what it is, a vehicle for near constant musical numbers. Additionally, there is opposition from a villain that is cartoonish enough to be family-friendly, but still realistic and threatening enough to properly fulfill his role. However, complaining and negativity are the bread and butter of analysis channels. However, the movie leaves me with only one real question that needs to be answered. What is the terminal velocity of a Besuited Koala? In all seriousness, this isn't a spoiler since it's in the trailer. Buster does get thrown off a building near the climax. However, koalas do have several evolutionary advantages that makes long falls less dangerous. Could Buster have actually survived being thrown off that building? To determine that, we'll first need to determine his terminal velocity. This is the speed at which the drag force in the air equals the force of gravity. Force of gravity is mass times gravitational acceleration, which is based off the size of the Earth, as it pulls down everything equally. Drag force is this complicated formula. It's based off the density of air, the cross-sectional area, and the velocity squared. We'll get into CD later, but it's effectiveness of the shape. So, let's set these equal and solve for v. Move over the 2, divide by everything, flip and root it, and we're done. Please note that this is proportional to the root of mass over area. This is why large, light things fall slowly, while pointy, hard things drop quickly. It's all due to air resistance. If there was no air, everything would fall at the same rate. And the astronauts actually did do that on Apollo 15. Back on topic. This is normally where we just plug things in. However, we run into a problem. CD is a constant derived from experimentation. This is based not only on the cross-sectional area, but how air flows around your object, and the vacuum that's created from the back of the object. A sail or a parachute will have a high coefficient, on the order of 1 or 2, while vehicles are designed to have a very low coefficient so they cut through the air without having to push it all out of the way. Unfortunately, I'm not game theory. I don't have a budget. And the Houston Zoo hasn't responded to me since my senior project into camelid antibodies. So we're not going to be able to put any exotic animals into wind tunnels. On the other hand, observations have been done with squirrels. And as they're both small, fuzzy mammals, it's close enough. Your normal squirrel has a terminal velocity of 23 miles per hour. Since they weigh roughly 1 pound, have a body 10 inches in length, and a tail almost as long, let's assume our squirrel is a rectangle, so based on our model here, a squirrel is roughly 3.5 inches wide. So, our squirrels have an area of 70 square inches. So, let's do some math. First, let's simplify our formula. Since gravity and air density are constant, we can collapse all the constants into this formula. Our terminal velocity is our new constant, c of k, times the square root of mass over cross-sectional area. This constant will be the same for anything roughly the same shape and texture, so let's call it c of k, the constant of the koala. Plugging everything into the formula, this yields a constant of 192 miles per hour times inches over square root of pounds. Don't worry about the units. As long as you're consistent on what you use, you can have whatever wacky units you like. Do it in furlongs. Everything cancels out in the end. But anyway, let's take our typical koala. Weight is 15 pounds. Cross-sectional area is around 480 inches. This means our koala has a terminal velocity of roughly 35 miles per hour. This is pretty fast, but overall, not too bad all things considered. Now, it wouldn't be pleasant, especially if you hit onto concrete, but a 35 mile per hour impact is survivable. especially if Buster can land on his feet on a soft surface. Koalas fall out of trees all the time and survive falls fairly regularly. To compare, using this drag coefficient, a human in a dive weighing 200 pounds, but with an area 2 foot square, has a maximum velocity of 113. But since we aren't fuzzy, we do have a lower drag coefficient, leading to an even higher maximum speed. So, this is how someone who has a significantly higher mass could catch up with Buster and do a Spider-Man save, even if they jumped into freefall after he was already fallen. Now, I'm not saying who does this due to spoilers, but they are wearing a spacesuit, so they would have a much lower coefficient of friction. All that being said, there is one thing working against Buster. The suit. A large part of the air resistance is provided by the fur, and a slick suit like Buster's, replacing most of his body fur, will speed up his terminal velocity. Hopefully the chibi proportions will help with that. So anyway, thanks for coming in with me on this dive through fictional physics once again. Thanks for listening, y'all. And a Merry Christmas.